Hello everyone, today I'm going to teach you how to calculate the bubble point using Priester's charts, and we have a multi-component mixture over here. And what we have are liquid mole fractions Xi, and we also have the total pressure. How do I know that these are liquid mole fractions and not gaseous mole fractions? I know that because bubble point is when a liquid turns to a vapor. So these mole fractions which are already present are liquid mole fractions. So that's why I know these are Xi or liquid mole fractions, and what we need to find are vapor mole fractions or Yi, and we also need to find the bubble point temperature. So I'll teach you how to use the Priester's chart and how to do a system of iterations to get closer to the most precise bubble point. Okay, so moving on, we have to find the K values, we need our pressure, our total pressure, which is given as 1 atmosphere or 101.3 kilopascal, and we need our temperature. We don't have our temperature, so we'll guess the temperature first, and then we'll do a number of iterations to reach the right temperature. So this is what we're going to do. We have in our this is our Priester chart minimized. This is our pressures given in kilopascal, and this is our temperature given. So what we're going to do is we're going to make a line connecting from our pressure to our first temperature. So I have taken my first guess to be 56. I'll explain later why I took my first guess to be 56. So I join from 101.3 till 56, and these are the K values which I'm able to read over here. So for example, for N-butane, this K value over here is 5.6. See, you can see this one is 5 over here. You can see this one's 5 over here, this one's 6 over here. So our K value over here is 5.6 for N-butane. And this is how we read K values. These charts are a bit difficult to read, and the scales and the demarcations are not regular over here. So you have to be really careful when reading these charts, but it comes with practice, don't worry. And then moving on, this is how we read the Priester chart. Moving on, let me explain to you how we get the right iteration. So first, we choose a temperature, and then we read our K value, and then we check if the summation of product of Kx is equals to 1. If it's true, this means that the K at that particular T gives us the bubble point. If it's not true, then we choose a new K value, then we choose a new temperature or a new K value, either one of them, and join a line. And then we read other K values, and then we check if it equals to 1. If it doesn't equal to 1, we will continue our iteration again. So this loop over here continues for like maximum 2 times until we reach a value which is closer to 1. Now, going down, I'm going to tell you how we choose the first temperature. Now, our bubble point is going to lie between the boiling points of our, this is our most volatile component and this is our least volatile component. So our bubble point is going to lie between the boiling points of our least and most volatile components. So we know it's between -1 and 69C. But this is too large of a range. We can actually further narrow it down and choose a certain temperature which makes some of the K values greater than 1 and some of the K values less than 1. And why do we do this? I'll tell you why. Because let's say our X values are given over here as 0.2, 0.5. So let's say K is 1.5 over here. And then you add all of the values, 0.3, 0.5, let's say, and then let's make this 0.8. So I'm giving you test values over here, and after you keep on adding these values, you need some of them to be greater than 1 and some of them to be smaller than 1. So at the end of the day, all of them should equal to 1. Why should they equal to 1? I actually explained this in my last video, and they should equal to 1 because all vapor mole fractions and all liquid mole fractions in a mixture are equal. So this equals to this. But we need a certain relationship between the vapor and liquid mole fractions. So we write it as this. Y is equals to Kx, where K is the vapor liquid equilibrium constant, and thus summation of Y is equals to summation of Kx. Now Now, ideally, we need this and we need both of these to be equal to 1. So we need summation of kx to be equal to 1. This is why we try to pick a k value since all of our x values are less than 1, since summation of x equal to 1 because we're talking about a mixture and all separate components should add up to 1. Since our x values are less than 1, our k values need to be, some of them need to be larger than 1, some of them need to be smaller than 1. So finally, the summation of the product of x and k can be equal to 1. Hopefully I clarified my point. If I did not and you have more questions, please let me know in the comments below and then I can improve on my explanation. Moving on, so I over here chose the temperature. See, 69 is a bit too high and -1 is a bit too low, so I chose the temperature 56 because this gave me a range of k values. 2 of them are greater than 1 and 1 of them is smaller than 1. This is acceptable, but my k value still came out to be greater than 1, which means that my bubble point is too high. It means that my T needs to be lower. So I need to choose a new K. And now I'll go back to how I read off these values, N-butane, N-pentane, and N-hexane, going on for T is equals to 56. So I made a line over here at 101.3 and at T is equals to 56. And my first value was 5.6, then I got 1.85, then I got 0.69. Let's see if I'm getting the same values over here. For N-butane, my first value over here, see this is the graph of N-butane over here. This is N-butane and I'm getting 5.6. For N-pentane, over here we can see these graphs, the demarcations are not linear, so we have to be very careful when reading them. As you see, this is 0.9, this is 1.0, this is 1.5, and this one is 2, this one is 3. So my graph over here is 1.85. This is 1.5, it's between 1.8 and 1.9, so this is going to be 1.85 as I have written over here. Now let's read for N-hexane. Let's follow this curved line for N-hexane. The demarcations are actually not linear because the lines are curved over here, as you can see. For N-hexane, it's 0.6, and as you can see, this is 0.6, this line is 0.6, this is 0.7. So you can see our demarcation our line cuts over here, which is very close to 0.7. So the value I've taken it as 0.69. And this is my first trial. I've marked this as T1. Now, when I've gotten my x1 and k1, I'm gonna calculate its product and I'm gonna take the sum. This sum came out to be much greater than 1, so I need to choose a lower t. And I can do this with the help of an equation, and this equation actually just comes from the fact that the summation of all components should equal to 1, and I'm gonna rewrite it and explain it over here. So this is how we calculate this equation. Since summation of ki xi equal to 1, so what we do, ki xi new should equal to 1, and ki xi old is something which is much larger than 1. Now what we're doing is we have a k reference, which is one component that we've picked out, and then we have a k reference new. K reference new, one component that we've picked out, and then here it's k reference old. So let's say over here I've picked out pentane. I've picked that out as the specific reference component, and this I calculated this value. This value came out to be 2.52. This value over here should be 1 ideally. So what I'm trying to do is I'm trying to take the ratio of the k values of pentane, the new value and the old value, and then I'm comparing that against the ratio of the summation of the new value and the old value. This is 1 and this value over here is 2.25. So this is how I get the new k reference value. I calculate the new k reference value because this value over here is given. I just read it off the charts. This value is the product, and this value is the 1. This value is 1. And as we see, the K reference value is 1.85. This is something we calculated. So the new value that ideally should belong if K1x1 new is equals to 1 is 0.82 over here. So now what I'm trying to do is I will draw a second line which connects 101.3 kilopascal and K reference or K pentane is equals to 0.82. So this is what I'll draw a line, and I'll prepare a second table. Okay, I drew a line from 101.3 to N-pentane. N-pentane over here is this one, and what was the K value? My K value was 0.82. So over here, this is N-pentane. This chart I'm trying to follow. This is, let me magnify it so it's like easier to read. So over here, we see this chart's a little bit hard to read. This one is 0.7, this one is 0.8, this one is 0.9. So over here, somewhere over here lies 0.82 for N-pentane. So I need to pick this point here, and I need to pick this point here, and I need to make a line between these 2 points. Then I'm just going to extend this line, and I'm going to call this T2, and it cuts the graph at 30. And at 30, this is my new temperature. Now, from this new line, I'm going to read off new K values for N-hexene, which turn out to be this is 0.2, this is 0.25, and this is 0.28. So this turns out to be 0.28, and for N-butane, the value turns out to be 0. This is 2, this is 3, so the value over here turns out to be 0.29. Let's see what are the value I have found. Yes, 2.9 and 0.28. So these are the new values that I found. Now again, I'm going to calculate the product, and I'm going to write the summation of the product. Here, my value came out to be pretty close to 1.074, but it's still not equal to 1. So I am going to calculate a new K value using the same similar formula over here. K ref new is equals to K reference of old divided by the summation number. Now it's telling me to calculate the new K ref as 0.76. Previously it's at 0.82. Now it's saying 0.76. So what I'm going to do is I'm going to do a third iteration, and I'm going to make a third line. Now let me make a third line. Here I'm going to connect for N-pentane. Now my reference component is going to be the same. It was N-pentane over here for 0.76. So I'm going to connect 0.76 and 101.3. So 101.3, and for N-pentane it's 0.76 over here. So this is 0. No, not this one. This one is 0.76 over here. Let me increase the magnification. Where is N-pentane? Yes, here's N-pentane over here. Now this is 0.3, 0.4, 0.6, 0.8. Yeah, this is 0.8 over here. You can see this one is 0.8 over here, this one 0.7 over here. So 0.76 comes somewhere over here, and this is how I have connected this line. So this is 0.76, and this value that I circled before, this is the new K value for N-butane. And over here, coming down from here, this is the new value for N-hexane. Now I'm going to read both of these. This value is going to be 0.25, and this value is going to be around, this is 2.5, this is 2.3. So this value is going to be around like 2.7-ish. Yeah, 2.65, pretty close. So this value is going to be 2.65, and for N-hexane, I said it's 0.25. And we made a line between 0.76 and 101.3. And then we just extend this line and we call this T3, and we see that it cuts the graph at 28 degrees Celsius. Now, I realized that my reference value, one of my reference value was 0.76 and one of them was 0.82. So my K values cannot get much closer, like, because then there is not much space in the graph for them to get closer. You see, this is the pentane curve over here. There's not much space for them to get closer. This is the closest I can get with the Priester's chart. So now when I just extended my line, I called it T3, and this is how I just calculate my bubble point as 28 degrees Celsius. This is the closest I think I can get with Priester's chart, because of the limitations of lines. Like you see, both of these, like you see, where is n pentane? Yeah, both of these new values are pretty close to each other, even though the effect is much magnified when you come and increase the line. Like it's a difference of 2 degrees Celsius between 30 and 28. But when I'm here, my lines cannot get more precise than this. Like it's very hard, and this is through magnification. Imagine when we're doing it on paper, it's a little bit harder. So this is the closest I can get with Priester's chart, and I got my T bubble as 28 degrees Celsius. Now I wanted to check my answer, so I used an app thermosolver, and I got the bubble point as 28.91 degrees C. This is pretty close, and it just gives me confidence that my method is correct. Hopefully you guys understood this method, and don't forget to leave a comment. And please comment on my teaching style. Please let me know if there's any more questions you want me to follow or any more videos you want me to do. Thank you for listening, and I'll see you later. Bye.